This is section 11.1, sequences and series. This is a whole new topic for us, and in this course we're just going to get a brief introduction to this concept of sequence and the concept of series. In a later class like Calculus 2, you really go into really a deep analysis of these things. But here we give you that overview of it, so when you get there to Calculus 2, it doesn't feel totally unfamiliar. So let's start at the beginning here. What is a sequence? When we describe a sequence, if you said the word sequence to a mathematician, probably two different things come to mind. One interpretation, and one I think you'll work with commonly when you see a sequence, is just a list of values. So maybe like 1, 2, 3, 4, 5, and so on. Or maybe, I don't know, 2, 4, 8, 16, 32, and so on. So a sequence can be thought of as a list of numbers in a very specific order. 1, then 2, then 3, then 4, 2, then 4, then 8, then 16, and so on. I've written ... at the end of these that implies that these keep going on and on and on, and there's no end to this list. That would be what we call an infinite sequence. If it's just a finite list, like 5, 10, 15, 20, and I stop it there, that we would call a finite sequence, because there is a finite number of these, only 4 of them. There are infinitely many terms in these infinite sequences. So this is one way to think about it. In plain terms, it looks like just a list of numbers in a very specific order, a list of values. But really, a mathematician might also say, well, that is just a description of a function whose domain is just the set of the first n positive integers. In the case of this n equals 4 ordered values. Or there are 4 values here. The first one, the second one, the third one, and the fourth one. So you could view this as a function where 1, 2, 3, and 4, the position in line, is your domain value, just a set of integers. In this case, we have n equals 4 of these. So your n is like the number of terms in your list. Right, in this case, you could say, well, if I plug 1 into the function, I know it returns a 5 in that one position. Right, so there's a deep connection between the position in line, this integer, and the value that's sitting in that position. That's like the output of your function. Well, you could do this also where you have an infinite sequence, like one of these up here, where it's not just an input value of 1, 2, 3, and 4 in the domain, but there are infinitely many integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way out to trillions and billions and quadrillions, millions of millions, all the way out to anything, to any infinitely high value. But as long as it's an integer, right? All the positive integers would be the domain. And an infinite sequence because there are infinite positions to be filled. Right, the terms of a sequence are denoted by a letter A with a subscript representing the number in line. So for example, in this sequence I've drawn here, or I've written out here, we would say A1 equals 5, A2 equals 10, A3 equals 15, A4 equals 20. So in other words, this is exactly like a function where instead of having something like f of x equals some expression in x, like x squared, we would have something like f of only the integers equals something like that integer squared. But we would just write that result as an instead of f of n. So it's just a different form of function notation. We're really saying an is equivalent to whatever our function is evaluated at that n. Right? So it's a different name, it's a different naming system for these function values. Right? And when we want to describe this sequence as a whole, we would use just a general description of what the nth term looks like in set brackets. This is like writing f of x, where you're not specifying the input value, you're describing the output in terms of that input. Like x squared, for example, tells you how to get the output from the input x. So we'll see some examples of this to hopefully clarify the situation. Yeah, let's go on a little bit. This is a good example here. Let's write the first 4 terms of the sequence defined by the nth term given here. What do we mean when I say the nth term? Well, we're just saying that whatever term in line, we usually call this an index value, whatever number of term in line we are, the first, second, third, fourth, and so on, we're thinking of how do we describe a position in line without specifying the actual number it is. Well, we could say the first position in line sits here, the second sits here, the third sits here, the fourth sits here, then the 5th term, then the 6th term. And if we want to go up to an unspecified term, we're just putting a number instead of these numbers that represented the number in line we were. So we'll just say an unspecified number n in line. The nth term is in position n in line. So if we want to describe a function, this is a nice way to do it. Describe in terms of your position in line, in terms of this domain value n, what is the sequence value we have. So this is going to be pretty, the description here mathematically is much more complicated than what it feels like we're actually doing. For example, here, this first problem, if we want to write the first 4 sequence terms, all we're going to say is plug in the first term. That would be n equals 1. Right, because it's position 1 in line. That's just a1. Since n is 1, I'm plugging in 1 squared. The second term, that would be n equals 2 because it's in the position 2 in line. And that's saying n is 2, so I'll plug in 2 squared plus 5. And so on. A3 would be 3 squared plus 5. A4 would be 4 squared plus 5. And we can see what these equal. 1 squared plus 5 is 6. 2 squared plus 5 is 9. 3 squared plus 5 is 14. 4 squared plus 5 is 21. So those are our sequence values. We can write that this sequence of ANs starts looking like 6, 9, 14, 21, and keeps going on and on and on. We found the first 4 terms. Okay. And graphically, we have this represented to really make that connection between functions and sequences. This is exactly what we've plotted here. When we have the first entry, position n equals 1 here, we go to a height of 6 on our graph. And we just plot that single point. All of the points in between the integers are not defined for a sequence. So on this red graph, we get the sequence is just these dots here, right? When n equals 1, we plot a height of 6 because that's the position in, that's the value in position 1. In position 2, we have a value of 9, so we plot a point at height of 9. At n equals 3, the third position, we have 14, so 3 goes with 14, and so on. So we get this discrete set of points here instead of a curve that a regular function would give us. But what is the connection? Really all we're doing to get these sequence values is taking the input value, the integer n, squaring it and adding 5. So this is just like taking a function in general that takes an input value, a function f of x, that takes the input x and squares it and adds 5. right? These two functions are really doing the same thing to the input. The only difference is the values of inputs that we're considering. In the case of a sequence, we're just considering the value of our function on the integers 1, 2, 3, 4, and so on. For the function f of x, we consider any value between the integers perfectly acceptable as well, and that fills out all these other dots that make a smooth curve. But if you were to overlay these, let's see if we can do this. If you were to overlay these, yeah, those dots sit right on that blue curve. Right? Notice that. It was kind of cool in demo. Glad that worked. Didn't think that would work. Right, so that's the connection. These really are the same function. The sequence function, though, that we write with a little bit different notation, just says we're only allowed to plug in integers for n. Okay, so let's go up here, see a little bit more. Give myself some space there. Again, we just want to plot the first 4 terms of this sequence 3 times, where an, the nth term, equals 3 times negative 1/3 raised to the n power, where remember, n is just the position in line that you're looking at. So this sequence, well, in the first position, we'll put a 1 in. In the second position, we'll put a 2. In the third position, we'll put a 3. And in the fourth position, we'll put a 4. Right? And so we have to figure out what are all these values. Well, when n is 1, that means a1 equals 3 times negative 1/3 to the, well, our n value up here, that's a 1. Right? n is 1 in this case. Negative 1/3 to the 1 is just negative 1/3 times 3 is negative 1. A2 says plug in n equals 2. Looks like we get 1/3. A3 says plug in 3 for that power n. That's 3 times 1 over negative 1 over 27. That's negative 1/9. Finally, A4 says plug in A4 for the n value. You get negative 1/3 to the 4th power equals, you check my math here, I get 1 over 27 when I do this. Notice each subsequent term of this sequence seems really just to be the previous one divided by negative 3. Right? There's a nice pattern to these. It's just the previous one divided by an extra copy of negative 3. Or multiplied by 1 over, negative 1 over 3. You can think about it that way. A sequence like this actually has a very special name. This is called a geometric sequence, where between every subsequent pair of terms, there's a common ratio to them. In this case, it would be negative 3. Yeah, it's just that easy, though. You're just plugging numbers in. We know how to do this. So do notice here a pretty important fact that the negatives, the signs of these terms, keep switching. Every term you go negative, positive, negative, positive. It'll keep that pattern up. And that's caused by having a negative inside of this n power. What do we really have here? Our nth term, as this is called the nth term, let's be clear, of the sequence. When we write it out this way, instead of calling it f of x, we call it the nth term. That's all it really is. It's like the function description. An equals 3 times negative 1/3 to the nth power. Well, look how we can write this. We can write this as negative 1 times 1/3 to the nth power, which is 3 times, that power goes to each of these factors individually. Maybe even I say, well, that this 3 is really a 1/3 to the negative 1. So I can put it with the 1/3 to the n out at the end. You wouldn't have to do that. You'd never have to do this, but we could combine that and say it's n minus 1 powers of 1/3. What I really want to see is that we separated out this negative part of the base raised to this power. Remember, when we talked about exponentials, functions that kind of look like these guys, we said we never allowed negatives inside of the base of an exponential. It's perfectly allowed with the sequence. Turns out that's only a problem for fractions for your input n, for your input power. But still, it's nice for very clear reasons that we'll see to separate out that negative stuff from the base at least, like we've done here. I've got negative 1 to the n times some positive stuff to some n related power. Well, notice what this term does. The positive 1/3 raised to any power is still positive. So this is just a positive contribution out here. But the negative 1 to the n, I call this an alternating factor. Because think about the values that just this sequence would take on. Right? Think about what just this little part does to the overall sequence. This guy's sequence values would be when n equals 1, we get negative 1 to the 1, which is just negative 1. When n equals 2, we get negative 1 squared. N equals 3, we get negative 1 cubed, and so on. We're running out of room, and it keeps going, right? But look at this pattern. Negative 1 is negative 1. When we square a negative, we get positive 1. Odd power of a negative gets a negative 1. Even power of a negative gets a positive 1. Odd power. Next would be an even power, then odd, then even. This guy alone, what I'm calling an alternating factor in a sequence, it will just, with every subsequent term, just flip the sign of everything from a positive to a negative to a positive to a negative and so on. So this alternating factor takes whatever the 1/3 to the n minus 1 is and just makes sure that at every term it's flipping signs, positive, negative, right? So the 1/3 to the n minus 1, those values would just be 1, 1/3, 1/9, 1/27. The flipping of signs between all of them is caused entirely by this negative 1 to the n. Right? For such a reason, this is called an alternating sequence. I call this particular little factor inside of here, the negative 1 to the n factor, I call that an alternating factor. I believe you'll hear that occasionally from other people as well. Okay. Yeah, and this is exactly describing what I was getting at. Notice the negative 1 to the n, what we had here, that starts with a negative, then goes positive, then negative, then positive. Well, so that is negative, positive, negative, positive. If we wanted a sequence to alternate oppositely, positive, negative, negative, how would we cause that? Well, we just actually add 1 to those powers that are stepping up by 1 unit every subsequent position in line we look at. Right? We just add 1 to that. Because we can see how this will work. If I plug in n equals 1, let's look at this other alternating factor. When I plug in n equals 1, I have 1 plus 1 is a power of 2 that we're starting with. N equals 2, n equals 3, and so on. Well, even power makes positive, odd makes negative. Oops. And so on. So we see how just adding 1 to that alternating factor's exponent really just makes this work in the opposite direction. Starts you on a positive, ends up on a negative. Okay, so let's go a little further here. Another way we could, let me back up. What we would probably call something like this up here, where we're describing the nth term with a little formula, I would call this an explicit description of the nth term, right? You tell me what term in line, what number of term in line n you want, I can plug that into this formula and you can figure out what term sits in that position in the line. This is called an explicit formula. I would say there's other ways to describe these nth terms in line, one of which is called a recursive formula. Not an explicit formula, but a recursive formula. It defines the nth term in line in terms of previous terms in line. For example, what we're seeing here, right? The first four terms of the sequence defined by this recursive formula. A1 equals 3, and an equals 4 times an minus 1 minus 2. So if this guy, an, is in the nth position in line, let's kind of draw this out. First position, second position, somewhere out here, n is some unspecified value, but it's some number, n out here. Well, the n minus 1 would be just the position just before that. Right, so that if n was, I don't know, 20, then the one right before it should be, well, n equals 20 minus 1. Should be the position that comes just before it. So this is how we describe the position just before the nth position. Right, we use an n minus 1. So in this way, we have a description for the nth term here written in terms of previous values in the sequence, the n minus 1, the term that came right before it. And so now maybe you might see why we need this starting value. For example, if I wrote down, say we didn't have this a1 equals 3, and I set out to use our recursive formula to find a1, well, then this formula would tell me n equals 1 is what I'm looking for, meaning I have to plug in 4 times a n minus 1. That would be 1 minus 1 minus 2. Well, we have a problem. 1 minus 1, that is saying that a1 equals 4 times a0 minus 2. Right? 1 minus 1 is 0 as our index. So that's a term that comes before the first term. That term isn't something we have, right? It's not something known. Occasionally you will actually define sequences that have index values less than 1, like 0 or even negatives. But here we weren't given any information about this previous 0th term. It doesn't exist in this little world we're living in here. So we wouldn't be able to just use this recursive formula over here to find the first term. There has to be some starting point given to us. That first term has to be just given to us for a recursive formula. We have a starting value, and we have a way to always get to the next value from that starting value. That's how recursive formulas work. So let me clean up my mess here. And let's actually do this problem that's asking us to write out the first 4 terms of this recursive sequence. A1 is the first term. That's given, that just equals 3. A2. Keep in mind, that says we're looking for an n value of 2. So plugging into this formula, we'd say A2 equals 4 times a n minus 1. n equals 2 minus 1. Minus 2. And what is this? This is 4 times 2 minus 1 is 1 on our index, minus 2. And this is exactly what we need. A2 is described in terms of A1, which we know a value for. A1 is 3, so we get this pretty easily. 4 times 3 is 12, minus 12 is 0. A2 equals 0. Write that up here. We have the first term given to us. We've now got the second term. That lets us solve for, when n equals 3, lets us solve for the third term. Well, that would say we need 4 times a2 minus 1. Right? That's what this recursion is saying, this recursion formula. So that's 4 times a2 we know is 0. Minus 2. 0 minus 2 is negative 2. And finally, we look for A4, the n equals 4, n equals fourth term. So that will depend on A3. Right? 4 minus 1 is the third term. So that's 4 times A3 we know to be negative 2 from the previous line of work. Minus 2 at the end equals negative 8 minus 2 is negative 10. So A4 equals negative 10. We have found the first 4 terms. A1, A2, A3, and A4 equal 3, 0, negative 2, and 10, respectively. A popular sequence, moving on a little bit, a popular sequence is the Fibonacci sequence. You may have heard of this. It is defines something called the golden ratio. Pretty interesting topic, but it's a pretty classic one and a simple one that is often represented as a recursive formula. Notice this recursive formula down here, an equals an minus 2 plus an minus 1. So notice the nth term here depends on not just the one before it, an minus 1, but also the one before that, an minus 2. So it's the next term in line is always the sum of the previous 2 terms in line. Well, since that depends on 2 previous terms, you actually need 2 previous starting values for this. Then if we were actually to check this out, right, A1 and A2 both equal 1, so we put those here, first terms in line. The third one, right, A3 would be A1 plus A2, the sum of the previous. 1 plus 1 makes 2 here. Then in the next position, the fourth position, that's just the sum of the previous 2. 1 plus 2 makes a 3 here. In the next position, it's the 2 plus 3 makes a 5. In the next position, we have 3 plus 5 makes 8, and so on. This is the Fibonacci sequence. It turns out the ratio of one of these to the next one, as you let this sequence go on to infinity, it approaches something called the golden ratio. It's a pretty interesting idea. But it's a pretty popular sequence. These Fibonacci sequences show up everywhere in nature, in lots of spiral patterns. You might have seen the little spiral pattern representing this sequence. You start out with this box and this box. You just start adding boxes with dimension given by the sum of these 2 dimensions. So for example, add a box with the sum of those dimensions. Add a box with the sum of these dimensions. Add a box here, the sum of those dimensions. Squares, I should say, not just boxes, and so on. And if you think of making a spiral through here, it makes a very nice spiral that shows up in nature often. Right? This is very closely related to the golden ratio. You might want to look that up. Pretty interesting idea. These dimensions of each of these squares, the side lengths, follow the Fibonacci sequence. That first one was 1, the second one was 1, next one was 2, next one was 3, next one was 5, right? 1 plus 3 is 5. Then we have 3 plus 5 is 8 for this big one. Right? It's pretty interesting stuff. Makes a neat spiral. The next big thing we would need to talk about is the idea of a factorial. This is another operation that you can do, just like addition, multiplication, subtraction, all of the standard operations, except it is only defined on integers. You can't do this to fractions, at least not unless you get into some pretty wild mathematics and gamma functions and wild things you might not ever need or see. But a factorial is just a special type of operation. If n is a positive integer, the expression n factorial, written just as n exclamation point, it's read as n factorial here, is just the value of n you start at, times the value, the next integer lower, times the next integer lower, all the way down until you get to 1. And for technical reasons, the n equals 0 case, the 0 factorial, that's actually defined to be 1. So for example, we can jump in here, 5 factorial, that's an n value of 5. So it says start at 5, multiply by 5 minus 1, multiply that by 5 minus 2, multiply that by 5 minus 3, all the way down until you get to 1. Right? 5, 4, 3, 2, 1. That's what 5 factorial equals. So you multiply this out. What do we have? It looks like 5 times 4 is 20 times 6. It's like 120. 20 times 6. Yeah, 120. Okay. And these things come up very often in Calculus 2. This is the real reason we want to introduce it here. Factorial is a huge tool that we use in Calculus 2. We want to just recognize that when we see this exclamation point, it's just the number in front of it times the number in front of it minus 1 all the way down to 1. It's just a string of factors like this multiplied together. And it turns out some expressions have some nice cancellation that occurs when you have factorials, like a quotient, 6 factorial over 5 factorial. Remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Notice all this cancellation. The 4's cancel, the 3's cancel, the 2's cancel, the 1's cancel. All this really is 5 times 6. So it equals 30. That's quotient of factorials is usually a lot simpler than even the factorial alone, like 5 factorial alone. That's much harder to compute than the quotient because so much of that multiplication of factors gets canceled away. So let's see another one here. Maybe pause the video and try problem 6 here. See if you can simplify this down and see what it equals. I'm going to press forward though. 9 factorial, notice that is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial, factorial times 5 factorial. Notice what we have here though. This is just 5 times 4 times 3 times 2 times 1. This is 5 factorial. I don't know why I keep writing that wrong. This is 5 factorial here. So this copy of 5 factorial multiplied into the numerator cancels with this copy of 5 factorial multiplied into the denominator. And what we have left is 9 times 8 times 7 times 6 over 4 factorial. 4 times 3 times 2 times 1. So still, I would cancel as many factors as I could before trying to compute this thing. Starting in the denominator with the 4, I would cancel the biggest factor in the numerator possible with this 4. In that case, the 8. Moving down to the next factor in the denominator, with this 3, I would cancel the biggest factor up in the numerator possible with this 3. That would be the 9. Cancels and makes a 3 with the existing 3. Same with the 2. Can't cancel the 7 with it, but I can cancel the 6 with it. And so what do I have left over? Nothing in the bottom, just a 1. Don't even have to write it. In the top I have 3 times 2 times 7 times 3. Looks like this is 2 times 7 times 9. 7 times 9 is 63. Times 2 is 126. Not so bad. Now this next one's pretty interesting. This next one I think is a really useful one to see in preparation for like a calculus application, Calculus 2 class. Well here, what do we have in the top? We're not told what value n is, but we have an expression for what this factorial breaks down into. Right? It's n times one number less than n times two numbers less than n, all the way down to 2 times 1. So we could look at what this n factorial is here. That's n times n minus 1, n minus 2, n minus 3, all the way down to 2 times 1. And what is the n factorial? N factorial is n minus 1 n minus 1 less than that is n minus 2, 1 less than that is n minus 3, all the way down again till we get to 2 times 1. So we're getting all the same factors past this n minus 1 term. We just get n, right? N factorial over n minus 1 factorial is just whatever n itself equals. Right? This is a nice thing to understand in general, that you can always list out however many terms of a factorial you want, and then stop on one of these factors, list out as many factors of the factorial as you want, and stop on one of these factors and just express that as a factorial. For example, if I want to write, I don't know, 10 factorial a little bit differently, I could write out as many factors as I want, 10 times 9 times 8, and just stop whenever I want. Maybe I want to stop here at 6. All I have to do to make this accurate is put a factorial on the one that I stop at. Right, because that 6 factorial picks up the rest of the factors. 5 times 4 times 3 times 2 times 1. 6 times 5 times 4 times 3 times 2 times 1. Right, this little trailing end is picked up if I just put a factorial there. So all I really did up here is I said the n factorial in the top was n times, I'll only keep the first term, I'm going to stop on the second one in line, on this guy. I can do that by putting a factorial on that term that I stop on, the factor I stop on. And we know in the bottom I already had the same thing. So they canceled to give me n. These are some tricks that are involved in all this stuff. Don't hesitate to just write out the factors of these factorials and cancel one by one, especially when you're first getting used to this stuff. Eventually, you'll very naturally want to make these little jumps and cancellations. Okay, so let's try this one. Given the sequence defined by an equals 3n factorial over n cubed, let's find a3. No big deal here, right? Just plugging in n equals 3. 3 times 3 factorial over 3 cubed. What is this? This is really 9 factorial up here. 3 times 3 is 9 inside the factorial over 3 times 3 times 3. Right, 3 cubed. I'm writing it out like that, the 3 factors multiplied, in anticipation of canceling with some of the factors wrapped up in that factorial up in the numerator. So let me write it out. 9 factorial is really 9 times 8 times 2 times 2 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, so we start canceling stuff where we can, right? The 3 times 3, that's the same as a 9. The 3 here, maybe we just make this a 2 where we could cancel with the 6. And see what remains. What do we have? 8 times 7 times 5 times 4 times 3 times 2 times 1. 8 times 7 times 5 times 4 times 3 times 2 times 1. So I guess I'll just calculate this really quick. Let's see, this is probably, you could do this easily by hand, but it would take 2 seconds, so I guess I'll skip it. I get 6720 when I compute this on a calculator. So A3 equals 6720. Really nothing to it here if you see what a factorial really does. Okay, moving right along here, we want to talk about summation notation. This is where we start talking about series as opposed to just sequences. And the two ideas are very closely related, but a sequence we want to think of as just being a list of terms, or a function that spits out some terms. A series is what we get if we start adding those terms up. So in order to do that, we need something called summation notation, something to help us take sums in a nice, convenient way to express it mathematically. So the sum S of the infinite sequence, here we're thinking of a sequence that has no end, right? It just is an infinite list of values in a particular order. The sum S for the infinite sequence of ANs where the first term's A1, second's A2, and so on, is called an infinite series and is represented by this expression, S equals A1 plus A2 plus A3 plus dot dot dot. That's how we indicate that the sum keeps going. We put that dot 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 way out at the end. The sum of the first n terms of the sequence is called the nth partial sum. So this is like taking a finite sequence, just the first, I don't know, maybe n equals 10 terms, adding that finite sequence up, that's called the nth partial sum of this full infinite series, infinite sum of all the infinitely many sequence terms. So we call that S subscript n to tell us how many terms we took. S10 would be the sum of the first 10 terms. S20 is the sum of the first 20 terms, and so on. So notice that is just a finite number of terms. 10, 20, not infinitely many though. One of these partial sums is a finite sum. We call that a finite series, right? We call this infinite sum an infinite series. Let's call the finite sum a finite series. And here's where we get to this summation notation. This Greek letter sigma is a letter used to represent one of these summations, adding all these terms of a sequence up. Whether it's infinitely many or finitely many, we can use this summation notation written here to express it. This nth partial sum of a sequence of ANs, A1, A2, A3, and so on. If I want to add the first n of them, I'm going to add the ith term in line. Instead of the nth term, let's refer to the ith term, where I is any value from 1, written at the bottom of this sigma symbol, all the way up to I equals n. So that means into this AI, we're plugging I equals 1 to get the first term. Into this AI, we're plugging in I equals 2 to get the second term. And we go through all those I values until we get to up to n. So we go to 3, 4, 5, 6, all the way up till n. That describes n of these terms of our sequence added up, right? What we define to be the nth partial sum. But this symbology here, how we write this, is the important idea here. Sigma with an I equals 1 at the bottom and n at the top, right? Where the I value, the index we call it, starts and ends. Starts at a value of 1, ends at a value of n. The number we set it equal to at the bottom is called the lower limit of summation. The number we put at the top is called the upper limit of summation. You can talk about these with an unspecified number n plugged in there like it is here, but typically for like your homework problems, you'll have an actual whole number there, like a 5 or something, telling you that you're adding up the first 5 terms. But this sort of notation makes it nice for actually handling even unspecified numbers n of terms added up. Now, keep in mind that's a limited case, right? We're only taking n of these infinitely many terms, a finite collection of these infinitely many terms of our original sequence. If we take this n value and put infinity there, that implies that we're never stopping. We're taking every single term of the sequence and adding them up. And you might say, well, you add infinitely many things. Isn't that just infinitely big? Turns out not always. Sometimes you can add infinitely many finite objects and get something finite. We'll see you'll see in like a Calculus 2 class, there are very strict conditions on the function here, this AI function, that will determine whether this comes out to a finite value or not. You'll learn more about that later. Okay, so this summation notation here to describe sums is pretty useful. I want to see some properties before we go into examples, because I'd like to actually use some of these in these examples. But it says if we've got some sequences that we're thinking of adding up, sequence of ANs and a sequence of BNs, and C is any just number, like a 10, just a constant, then if we add a summation like this, a constant, not a sequence value, a constant added from I equals 1 to n. Well, what does that really mean we're doing? It means when I say a constant added from I equals 1 to n, I equals 1 to n, it means I equals 1 just sees this constant being added. When I equals 2, I just see this constant being added. When I equals 3, I see it again. And it doesn't change. All of these copies from I equals 1 all the way out to I equals the nth term. So there's n of these terms. Every one of the terms in that sum is just that constant value. It doesn't change as the position in line changes. So it's just this constant added to itself n times. That's by definition just multiplication, c times n. So it's exactly what it says here. Adding a constant c to itself a total of n times. That equals c times n. Right? When we say we have these subscripts I on these guys, that's saying as I changes, the function value, right? The output changes. When we put those subscripts I on these a values, it means a depends on I. So what if we have a constant times a sequence, c times ai being added up, like in property 2 here? Well, think about what that would look like. That is just when I equals 1, we get c times a1 being added. For I equals 2, we need to add in c times a2. For I equals 3, it's c times a3, all the way until we get up to c times the nth a value. Clear some space. The nth one, right? The top index value. Well, this is just all the a's added together, but multiplied by c first. This is a finite sum. Works just as you know. You can factor that c out. So what do we have? We have got c out front, now multiplied on the sum over just the a values from I equals 1 to n. Right? Inside this sum, we don't have the c's multiplied. It's just the ai's being added up. So that's what this is saying. You could multiply each number individually by c first, and then add all the results. Or you could add all the sequence values and then multiply by c at the end. It can just be factored out of a sum. This is just basic factoring that we're doing here. Similar, and maybe you want to write this out and see in similar terms of what we did up here, why this is true. If inside of the terms of a sequence you've got sums, a sequence of ai's plus or minus a sequence of bi's. So for I equals 1, it's a1 plus or minus b1 inside of here. Added or subtracted works. Then it turns out you can break up into the sum over the ai's plus or minus the sum over the bi's separately. So you could add or subtract all these terms individually, then add over that sequence you get from those individual sums and differences. Or you can add over the ai's, add over the bi's, and add or subtract appropriately. So a single sum or difference can be regrouped as two sums of differences. So let's see how we can use these to help us solve these problems here. For example, here, the sum from k equals 1 to 3 of 3k minus 8. Well, where's our I? It doesn't matter. This is a dummy variable. We call this a dummy variable. Whether we call it an I, a k, a j, any letter will work. It's the positioning and the relationships of these symbolically that makes it important. Right? Call it whatever you want. It's whatever values here should be the same value that we see the sequence terms inside expressed in terms of. Right here we're just saying our AKs equal 3k minus 8. That's our formula for the kth term. And this is telling us add it up. 4k equals 1 through 3. A1 plus A2 plus A3. Notice when we write out these terms, the index value gets replaced by numbers. We didn't care if we called it an I or K or whatever. When we write this out, it's really getting replaced by just values. It's a placeholder. We don't really care what we call it. I, K, whatever you like. So instead of solving this more directly, I'm going to use my properties to try to solve this one. Sorry, clean my space up here. Let's use some properties. Here's a difference embedded here. We know, according to property 3, we can split this up into the sum of the first piece, sum of the first piece, minus the sum over the second piece. And what else can we do? Well, in the first piece, we do have a term that depends on k. So that's like our ai up here, dependent on I. But we've got a number 3 multiplied on that term that depends on k. Right? Here's a k variable involved. So that thing's like our ai. But here the c, that's like the 3 here multiplying. We know that can just be factored out. Something independent of your index variable k here can be factored out from, just like it would from a regular sum. So we really have 3 times this sum minus, well, look what we have here. This is just a constant being added. So we can pull that out, or say it's, what is this? Yeah, what is this? This is saying we're going from a starting index value of 1, which we are, to a value of 3. Well, a value of n. Our value of n is 3, since that's where we're stopping. So we know we just get the constant that's inside, which is our 8, times our n value, right, times our n value of 3. So that's what this part of the sum adds up to, which is 8 times 3. All right, let's see what we've got. 3 out front times, I'm just going to write this out. When k equals 1, I'm adding a 1 here. When k equals 2, I'm adding a 2 here, right? Plug it in, you have a 2 sitting here. For k equals 3, we're adding a 3 here. And that's where we stop, right? We only go up to k equals 3. Minus the 24 at the end. 8 times 3 is 24. What do we have? 3 times, looks like 6 sitting here. Equals 18 minus 24, which is negative 6. So this sum, if I did add up all these numbers, equals negative 6. Now, I just did it this way to show you how these properties are used, but you don't have to do stuff like that, right? You could just plug in k equals 1 into this expression. So I'll say maybe an alternate way to solve this. Or you could just take this sum and plug in the starting value, 1, into this. You get 3 times 1 minus 8 is negative 5. Plus the next integer, 2. Plug in 2 into this, you get 3 times 2 minus 8. 6 minus 8 is negative 2. And then finally the top value we get to is 3. That's the next integer up. Plug in 3 into this, you get 3 times 3 minus 8. That's 9 minus 8 is 1. So what do we have here? Negative 5 minus 2 plus 1. It's negative 6, right? The same value we got before. I just wanted us to see how these properties can help us. Typically, it's actually, or how they can let us manipulate how these sums look. Typically, this is useful when you have an unspecified n up here. It lets you re-express these in pretty strange ways, pretty useful ways. But if I'm just adding up 3 terms, I'd probably just plug them in like we did down here. Right? K equals 1 term, k equals 2 term, and the k equals 3 term are being plugged in to be added. Okay, so maybe pause the video and try problem 10 here. Same idea, you're adding from I equals 1 to 4, you're adding the value of 2i over I squared. I'll press ahead. Hopefully you've had a chance to pause and try this if you want. Sum from I equals 1 to 4. Notice I've got I and I squared here. That's just 2 over I. There is no need to carry that redundant factor of I in this sum. Whatever I'm plugging in for I, it's going to cancel the 1 in the top with the 1 in the bottom. So let's do 2 over I instead. That'll be much simpler. So here I'm just, all I'm going to do is maybe one little simplification. I think this one actually will be a little bit helpful. I'm going to say this is sum from I equals 1 to 4 of 2 times 1 over I. I'll rewrite that. 2 over I is 2 times 1 over I. I'm doing that so that now I see this as a constant times something that depends on my index I. The constant can come out of the sum and multiply out front. It makes it just one step simpler to write out the terms here in this sum. So I've got the 2 out front, and now I'm just one at a time plugging in all the I values between 1 and 4 into this expression and adding each of them up. When I equals 1, I'm plugging in 1 over 1. When I equals 2, I'm plugging in 1 over 2. When I equals 3, I'm plugging in 1 over 3. And for finally, top value, biggest I go, is 1 over 4. So this is what I need to add up. This isn't so bad. Let me add all these. Looks like I get 1 plus a half plus a third plus a fourth. Do this how you like. I'll add these fractions myself. Looks like I get 12 twelfths plus 6 twelfths plus 4 twelfths plus 3 twelfths. Pulling out the 1/12 factor to the front, you get 2 twelfths. And the sum of integers. 2 twelfths is 1/6. And inside it looks like I've got 10 plus 15 is 25. So that's what this sum equals. So I think that in that case, factoring out that 2 to the front probably did make this fraction arithmetic one step easier. But in the previous one, it was probably easiest just not to use properties, just plug in the values and evaluate directly. Let's try a couple more here. You can try these, maybe pause the video, give it a shot. I'm going to go ahead and jump in though. Notice here, all we're seeing is that we don't have to start at an index value of 1. Here we're starting at j equals 3 and going up to j equals 5. So what will this look like? Well, just the exact same process. I have, notice, an alternating factor. -1 to the, well, first term is going to start with the j equals 3 plugged in. So 3 plus 1 is 4 up here. 3 times j equals 3 in this first term of the sum. The next one will be the j equals 4, right? This is the j equals 3 term. J equals 4 goes into here to be added. 4 into my power makes -1 to the 5th. 4 plus 1 times 3 times 4. J is 4. And I'll quickly write out the last one. What do we have here? So let's see, -1 to a even power is positive 9. -1 to an odd power is negative 12. Again, an even power makes a positive again, 15. Maybe factor out a 3. And what do we have? 3 minus 4 is -1, plus 5 is 4. We get 12. Not bad. On this one, well, that's just adding up a constant 1 up to 4, right? So when n equals 1, don't be confused by the fact we're using an n down here. It doesn't matter what we call these symbols. The positioning in all this stuff, the relationship to each other, is what we need to focus on. So the fact that I'm using an n here where I used to use it for a different place, doesn't matter. We're just saying we're calling our index n now instead of I. And we are adding, when n equals 1, well, plug in n equals 1 into 10, you still have just 10, right? There is no n there. It doesn't affect the 10. When you plug in n equals 2, well, again, plug it into 10, it doesn't change 10, right? There's no n going in. N equals 3, and n equals 4. That's where we're stopping. Gives us 4 copies of 10 multiplied. This is what our property above, sum of a constant, we clean it up, it's all cluttered here. It's exactly what we're describing here. From a starting point to an ending point, adding up over a constant just gives us that constant times how many terms there were. In this case, 4 terms. 1, 2, 3, and 4 terms. So we get 40. Okay, so we've already noticed that we don't have to start at the same value. We don't have to start at 1 on these index values in these sums. We don't have to go up either. We could start at 0. We could start at different places. Let me do something, though, that will show that these two sums are actually the same. So that we can see a single sum, the sum of a given set of numbers, can be expressed differently with summation notation. There are multiple ways to express it. For example, here, let's take this guy and let's do a substitution. Let's do an index substitution. For example, we can let j equal I minus 1. What does that do? Well, I'm just going to take all of this thing and replace every term that's in I. I'm going to re-express it in terms of j. So what do we get? We're going from, well, i's lowest value is 1. And we know when I equals 1, plugging into here tells us j equals 0. So that's where j's got to start. And when we say I goes up to 4, well, we can figure out what j goes up to then. When I equals that highest value, we know what j equals. Plug in I equals its highest value of 4, we get j is 3. So that's how high j has to go. Now inside here, we're just adding terms I squared, but here we can solve for I and say I equals, just solving this little equation, I equals j plus 1. And so replacing the I squared with a j plus 1 squared gives us the exact same thing. So this is pretty neat. This is a pretty cool idea that we can really control what index value we start at by doing one of these index substitutions. This original sum started at 1. I wanted it to start at 0. A careful substitution there can enforce that, can make that happen. How would I have to treat, say, this one? What substitution would I have to do on this to get this one? What should k equal in terms of j? Let's see. Let k equal, well, I know when j is 0, I want k to equal 2. So let's let k equal whatever j is plus 2. So that when j is 0, I get k is 2. Well, then with that, let's figure out those new bounds. This guy, what does it equal over here? Well, at its lowest value, when j is 0, we set this up so that k is going to be 2. And when j is its biggest value, positive 3, we know k is, plug in 3 here for j, we get k is 5. So the k value should go from 2 to 5 if we want to express it in this new index k. Well, and what do we have here? Let's see. Let's see if I can make this come back to life. It looks a little strange. We had, if we remember, yeah, luckily I've got a copy because my document's acting strange. This is exactly the sum we have up here. We have j plus 1 squared. Well, we know j itself, lots of arrows, sorry about that. J itself is k minus 2 according to this equation. So I'll plug in what j equals in terms of k. Instead of j plus 1, we're going to do k minus 2 plus 1. Because that's what j equals, k minus 2 plus 1 squared. And what is this? It's the sum from k equals 2 to 5 of k minus 1 squared. which my document is acting strange, but if you can see, that's exactly this expression we have here in this summation. Okay, so let's move on and see if we can finish up by writing each of these sums, which are given just in terms of the finite number of terms being added up. We're actually seeing those terms. Let's try to write each using summation notation. So we're going to actually see a lot about how to write a general expression for the terms of a sequence while we do this, because that's really all we have in summation notation is an expression for a general ith term of a sequence being added up inside of the summation. So let's see if we can come up with these and see if we can do it here. So for this one, for example, I've got how many terms here? I've got 1, 2, 3, 4, 5 terms being added up. So let me say that I'm adding from I equals 1 to 5. I'm adding some terms AI, right? So I'm adding A1, A2, A3, A4, plus A5. So I'm saying A1 is this first guy, A2 is the next term, A3 is the next one, A4 is the next one, A5 is the next one. Now our job is to come up with an expression for what this looks like in terms of I, the position in line that we're at. I equals 1, I equals 2, I equals 3, I equals 4, I equals 5. I need an expression for this ith term. So let's start trying to craft this thing. Let's try to figure out if we can figure this formula out. Let's see what we can do. Notice every one of these terms is divided by 5. So that's easy. I can say every one of them has a division by 5. But what's going on in the numerators there? When I equals 1, I have a 2. When I equals 2, I've got a 4. When I equals 3, I've got an 8 in the numerator. When I equals 4, I've got a 16. And when I equals 5, I've got a 32. So what is the pattern there? Can we express these outputs, these numbers here, in terms of the inputs I that we're labeling them with? 1 goes to 2, 2 to 4, 3 to 8, 4 to 16, 5 to 32. Well, this looks exponential. We're doubling every time, right? This looks like the formula would be, for these numerators, I is going to 2 raised to the I for those numerators. When I is 1, we have 2. When I is 2, we have 4. When I is 3, 2 cubed, which is 8. When I is 4, we have 16, and so on. This works. That's an expression for the ith term in line, where I could be anything from 1 to 5. First term, second term, third term, fourth term, fifth term. So we're seeing how to write this. We know the sum that we started with up here could be written the sum from I equals 1 to 5 of our AI. There you have it. This is our answer. That is summation notation for that sum, for that finite sum, that finite series. Take a second and see if you can do these last two, 14 and 15 here. I'm going to go ahead and run through them. Pause if you'd like to give it a shot. This one, let's see, what is the pattern we're doing here? Again, we're going to sum from, it looks like we have 1, 2, 3, 4, 5 terms, just like before. Our goal is to express what the ith one looks like. So the I equals 1 term, the first guy in line, that tells us we get a half out. When I equals 2, the second term in line tells us we get a 1 out. I equals 3 tells us we get a equals 3. I equals 3, sorry, tells us we get a 2. When I equals 4, we get a 4. And when I equals 5, we get an 8. So what is the pattern here? Again, it looks like we're doubling every time. So we're just starting with some initial value and multiplying by 2 every time to get to the next one. Right, so this one I could think of as 1/2. This one I could think of as 1/2 times 2. This one I could think of as 1/2 times 2 times 2. 4 I could think of as 1/2 times 2 times 2 times 2, and so on. Maybe we've cracked it. Maybe we found that pattern. So what is this? This is 1/2 times 2 to the 0 power. This is 1/2 times 2 to the 1 power. This is 1/2 times 2 to the 2 power. So maybe we see the pattern. As we step up our I values, we're also stepping up these powers on 2 that we're multiplying 1/2 by. So it looks like the ith term would be 1/2 times 2 raised to the, well, when we were at a certain I value, the power was 1 less than that. So when we're at an I value, the power will be 1 less than that I value. It will be I minus 1. So that's what the terms we're adding up really look like. It looks like we have the sum from I equals 1 to 5 of 1/2 2 times I to the negative 1. There we have it. We're noticing the only work involved here is finding a pattern, a way to express a pattern mathematically. Some not trivial stuff. Last one here, last example. First thing I'm going to notice here is that this is an alternating sequence we're adding up. Right? Again, I'll say this is the sum from I equals, in this case we only have 4 terms, so I'll go from I equals 1 to 4 of some terms AI so we need to figure out what is a formula for these 4 terms that depends only on the position in line where it sits, the I value. Let's see here. First of all, I know this thing is alternating, and I know how to cause that. It's with a -1 to your index power. Right? That'll cause the plus minus pattern in this sum. Right? When I is 1, I get a negative. That's what I need. When I is 2, I get a positive. That's what I need. And it'll just keep flipping back and forth as needed. So we get that alternating factor there. Right away to take care of the plus minus. Now we just need something that has 2, 4, 8, 16 in a numerator and 3, 9, 27, 81 and so forth in the denominator. Well, what's the pattern here? Up here we're just taking 2 times 2 to get to the next one, times 2 to get to the next one, times 2 to get to the next one. This is exactly the same sort of pattern we had over here. We started out with some fixed value, 2 on the first one, and we multiply by 2 on every case to get to the next one. So what is the pattern for that numerator? I think it's 2 times, it looks like we're multiplying by 2 to the I minus 1. Right, so that when I equals 1, the first term here, we have 1 minus 1 is a 0 power. It just disappears. We just are left with our 2. When I equals 2, the next term in line, 2 minus 1 is a single power of 2, multiplying the existing 2, making a 4. The third term, I equals 3, that's 2 squared is 4, times the original 2 is 8, and so on. This pattern works. How about the denominators here? It looks like the denominators look like 3, 9, 27, 81. They're following the same pattern as the top, except they're starting with a 3 and multiplying by 3 every time. Well, so I'll do that. Same powers though. Single power of 3, 2 powers of 3, 3 powers of 3, 4 powers of 3. Single power of 2, 2 powers of 2, 3 powers of 8, 4 powers of... I'm saying that wrong. Single power of 2, 2 powers of 2, 3 powers of 2, 4 powers of 2. Same pattern as the bottom, so I know it takes the same general form, just with a different base. This cleans up dramatically though. Let me keep this as nice looking as possible. Notice here, 2 times 2 to the I minus 1. This is just 1 power of 2 multiplied on I minus 1 powers of 2. Right, you got to add the powers to put these together. This is 2 to the I minus 1 plus 1. Same down here, 3 to the I minus 1 plus 1. So what do we have? It's just 2 to the I in the top and 3 to the I in the bottom. I will mention, I guess I should have mentioned this earlier, the I we use for an index has nothing to do with the square root of -1. This I is just unfortunately referred to with the same symbol sometimes, this index value. It's not related to complex values at all, completely unrelated here. So now, what do I really have? I've got a bunch of different factors all raised to the I power. I've got a -1 to the I power, I've got a 2 to the I power, I'm dividing by a 3 to the I power. You can put all this together as -2/3 to the I power. Cleaned up dramatically, right? So it's easy to write our sum now. This sum we started with is the sum from I equals 1 to 4 of our AI value, which we said is -2, quantity -2/3, I should say, to the I power. That's it. So you'll practice more with this in the homework, but I hope this has given you a nice introduction to sequences and finite series. We defined what an infinite series is, even though we didn't see any here. Those are actually quite a bit more complicated to handle, these infinite series. You have to study limits a little more. All right, that's it for this video.